Welcome to The Explainer. Today, we're diving straight into the hidden, highly technical world of agronomy. Now, we usually think of farming as a strictly physical endeavor, right? Plows moving dirt, seeds going into the ground, rain falling from the sky. But modern agriculture has actually unlocked some incredible, invisible superpowers, and we are going to explore exactly how cutting-edge proximal sensing lets farmers read the invisible layers of a field.
Here is our roadmap for today. We'll cover 1. Farming's new sixth sense. 2. Measuring the electric earth. 3. Radar in the roots. 4. Farming with gamma rays. And 5. Sensing invisible plant stress.
All right, let's kick things off with Section 1, Farming's new sixth sense. So, unlike remote sensing, where we're using distant satellites out in space, proximal sensors get right up close and personal to give us hyperlocal insights. By operating at close range, these systems interact directly with the environment. They aren't just snapping photos, they're quantifying how the soil and plants conduct electrical charge, how they reflect very specific spectrums of light, emit natural radiation, and even how they withstand physical, mechanical distortion.
When it comes to actually collecting all this up-close data, we essentially rely on two main methods. We can gather massive amounts of data from sensors strapped right to a moving tractor, or we can use a continuous, stationary wireless network. And honestly, to truly understand the temporal dynamics of a farm, we need both. Those on-the-go tractor sensors give us a massive snapshot of conditions across the entire field at one specific moment, while the stationary networks give us continuous, minute-by-minute monitoring.
Now here is the absolute crucial takeaway, the real paradigm shift. We aren't measuring a physical drop of water or a scoop of organic matter directly. Nope. We are measuring physical properties like electrical charge or light reflectance, and then inferring the data. Through established scientific relationships, we use that invisible physical signal to infer the actual agricultural property we care about.
Moving right along to Section 2, Measuring the electric earth. Imagine making the Earth itself part of a giant electromagnetic circuit. Mobile geophysical tools send electrical signals straight down into the ground. But soil isn't just dirt. It's a highly complex mix of solids, liquid water, and trapped gases. So we measure its ability to conduct a charge, which is called its apparent or bulk electrical conductivity, or ECA for short. And the big takeaway here? If the soil conducts a lot of electricity, farmers instantly know there's a high concentration of salt, or salinity, down there.
And the real magic happens when all that raw, invisible electrical data gets transformed into a stunning, color-coded 3D topographical map. Instead of just treating an entire field the exact same way, which is super inefficient, a farmer can look at these mapped variations in conductivity and apply water, fertilizer, or specialized treatments literally only exactly where they are needed. It's a total game changer.
80. That number is huge for us. It represents the dielectric constant of water. Because it's so high, materials with high dielectric constants can hold their charge for a really long time, which is exactly how we predict soil moisture. To put that in perspective, dry dirt has a very low dielectric constant, but water sits all the way up at 80. So when we measure the soil's dielectric permittivity, we're basically hunting for that number. The closer the reading gets to 80, the more water is hiding right beneath the surface.
To accurately pull these different readings using frequency domain reflectometry, it's all about tuning the dial. We use low frequencies, anything under 50 Hz, to track conductivity and salinity. But if you want to know how much water the soil is holding, you have to crank up the frequency to measure that crucial dielectric permittivity.
Which brings us to Section 3, Radar in the roots.
Think of this as literal X-ray vision for farmers. By bouncing radar waves off buried structures, we can completely map out hidden root systems. Antennas on the surface send signals down into the earth, and they bounce back the second they hit the coarse roots of the plant. We get this incredible cross-sectional view of exactly what is happening underground without ever having to dig a single hole.
Ground-penetrating radar, or GPR, operates in that sweet spot from 30 MHz to 1.2 GHz. And it doesn't just find roots. Whenever these ultra-high-frequency waves pass through different materials, like moving from dense soil into an empty underground void, or a deep crack, or a pocket of hidden water, the reflection changes. It paints a perfect, invisible picture of the entire subsurface landscape.
All right, let's head into Section 4, Farming with Gamma Rays.
Now you might be thinking to yourself, wait, radioactive farming? Are we intentionally radiating our food supply? Are we trying to grow glowing carrots? The answer is a resounding no.
When we talk about gamma radiation in farming, we are absolutely not mutating crops or exposing fields to anything dangerous. We're actually using entirely passive sensors. Gamma rays are just shortwave radiation produced during the normal, everyday radioactive decay of atomic nuclei. By using passive gamma ray spectrometers, the sensors aren't emitting anything. They're just listening. They're safely tracking the natural radioactive decay of isotopes like potassium-40, uranium-238, and thorium-232 that are already naturally present in the dirt.
So, picture a tractor acting like a giant, highly sophisticated Geiger counter driving across the field. With a GPS auto-navigation system hooked up to the spectrometer, it continuously listens to the natural decay of potassium-40 in the ground. This generates a highly accurate map based purely on natural photon energy, helping farmers expertly manage their soil potassium, which, by the way, is an absolutely vital nutrient for crop growth.
Finally, let's move out of the dirt and into Section 5. Sensing invisible plant stress. Using visible, near-infrared, and mid-infrared spectrometry, we monitor how light causes individual molecular bonds to vibrate. When the sun's light hits the crop canopy, some of it gets absorbed and some is reflected back. By capturing the exact signature of that reflected light, we can literally see precisely what constituents a plant is absorbing, its exact chemical makeup, its photosynthesis rate, and even its water content. We then take all that optical data and combine it with physical, mechanical readings. For example, if a mechanical sensor tells us the soil has extreme shear strength and high friction, we know the roots are struggling to push through. Combine that penetration resistance data with ultrasonic and infrared thermal sensors scanning the crop canopy, and farmers suddenly have an incredibly powerful early warning system to diagnose and treat crop stress long before human eyes could ever detect a problem. And get this, it's absolutely incredible. When a plant gets stressed, its chlorophyll literally glows brighter in the red light spectrum. It's like an automatic, biological distress beacon. Chlorophyll happens to be the only natural substance that fluoresces in this specific red region of the spectra. By tuning our proximal optical sensors to look for this exact red glow, we can map out which plants are thirsty, diseased, or lacking nutrients well before a single leaf actually turns brown.
So, as we wrap up this explainer, I want to leave you with this thought. We are already mapping hidden root voids with ground-penetrating radar, tracking natural gamma radiation, measuring electrical conductivity, and watching stressed chlorophyll glow red. If we've already mastered these incredible invisible superpowers, what undiscovered forces will revolutionize the farms of tomorrow? Thank you so much for joining me, and remember to always keep looking beneath the surface.